Correlation and causation are two terms that are often encountered in statistics and data analysis. While they might seem straightforward, they could be more frequently understood or misunderstood. This video aims to explain these terms, illustrating their importance in statistical interpretation, providing real-world examples, and explaining how hypothesis testing plays a role in distinguishing between them. Additionally, we'll explore how Python can visualize this concept. Correlation is a statistical measure indicating the extent to which two variables fluctuate. A correlation can be positive, meaning that as one variable increases, so does the other, or negative, where one variable increases and the other decreases. However, it's essential to understand that correlation does not imply causation. For example, consider the scenario of ice cream sales and drowning incidents. Data may show that drowning incidents will increase as ice cream sales increase. This positive correlation, however, does not imply that ice cream sales cause drowning. Instead, a locking variable like hot weather might be the actual cause, influencing both variables independently. Causation, on the other hand, implies a cause and effect relationship between two variables. This means that a change in one variable directly results in a change in the other. Establishing causation requires more than just observing statistical relationships. It often necessitates controlled experiment or deeper statistical analysis. A controlled experiment in the laboratory setting, where one variable is manipulated and the other is observed for changes, can demonstrate causation. For instance, increasing a specific chemical might directly accelerate a chemical reaction. Understanding the differences between correlation and causation is important for several reasons. Misinterpreting correlation as causation can lead to erroneous conclusions and misguided decisions. Recognizing this distinction ensures that decisions based on data are reliable and valid. For instance, consider the correlation between the number of firefighters at the fire scene and the extent of damage caused by the fire. While there is a positive correlation, that is, larger fires have more firefighters present, it would be incorrect to conclude that more firefighters cause more damage. Instead, large fires require more firefighters. Hypothesis testing is a statistical method used to determine whether the observed correlation between variables is significant and not just as a result of random chance. This process involves testing for statistical significance by calculating the probability that the observed correlation occurred by chance. Controlled experiments where variables are manipulated and other factors are held constant can help establish causality. So now let's look at my code. I imported the necessary libraries. So to set up a plot, we are using this function. This function creates a figure and a grid of subplots with a single call. In this case, we are creating a figure with two subplots arranged in one row and two columns, and we're setting the figure size to 12 by 6 inches. The first subplot shows an example of correlation without causation. We created an array using the arrange function, which generates an array with evenly spaced values within a given interval. In this case, it generates an array from 0 to 9. We use the random function to add some random noise to the 1 value, making the data more realistic. And finally, we create a scatter plot. The second subplot shows an example of causation. We again create an array using the arrange function, but this time we calculate y2 by doubling the values of x2 and adding some random noise. This creates a stronger cause and effect relationship. And we create a scatter plot using scatter to emphasize the causation aspect. So for the correlation without causation, you see a scatter plot with points scattered around a line in a non-linear pattern. And this is due to adding random noise to the y values. This plot demonstrates a scenario where two variables x1 and y1 show a correlation. As one increases, so does the other. However, the increase is not uniform due to the randomness introduced. And the plot exemplifies how real-world data might display correlation without any underlying causation. So for example, in context, if x1 represents ice cream sales and y1 represents drowning incidents, the plot shows that both increases possibly due to a third variable like warmer weather, but one does not cause the other. Now for the causation, the second subplot also displays a scatter plot, but with a more defined pattern. The points are closer to the trend lines, indicating a stronger, more direct relationship between x2 and y2. This plot is designed to demonstrate a causational relationship. The trend line suggests that changes in x variable directly cause changes in the y variable. The scatter plot points align closely with the trend lines, reinforcing this cause and effect relationship. So in a scenario for this, x represents maybe the dosage of medication, while y2 represents the improvement in patient's symptoms. The plot suggests that increasing the dosage directly improves the symptom. The side-by-side placement of these two plots in a single figure makes it easy to compare and contrast the concept of correlation and causation. This visual approach is effective for illustrating these concepts as it provides clear and intuitive understanding of how correlation can be visually distinguished from causation. A loser relationship between variables indicates that they may move together. One does not necessarily cause the other in the correlation plot, while the causation plot demonstrates a tighter, more systematic relationship, suggesting a direct cause and effect link. So thank you for watching. Here are my references. Bye.